you listening?
Back to Fam Bam. Today's physics topic is universal gravitation. Alright, so gravity is present anywhere. Anywhere you have matter. Meaning that the object exerts a force on another object. The equation that we use to solve universal gravitational problems is F gravity, equals gravitational constant, mass 1 times mass 2 over radius squared. Right here we have the laws of the universal gravitation, which is force of gravity between two objects, which you can see on this diagram, two objects. Alright. Universal gravitational constant, which is 6.67 times 10 to the negative 11 Newton meters squared times kilogram squared. Is the force in this area that is pulling the two objects near each other. We always have mass 1 and mass 2, the two objects, in kilograms, that's the units. R is your radius squared, it's separating the two objects from center to center. So the center of this mass will be your R squared. Alright. Things to consider. Gravity acts between two objects, equal force in opposite directions. Always gonna have two objects in this example, because usually it's used in outer space. Mass must be large to notice a gravitational force. Fun fact: the Earth doesn't notice our individual pull on it, but we notice its pull on us. That's why we can't fly. So that's basically saying that our gravity doesn't impact us as individuals, doesn't impact the Earth as much as the Earth impacts us as individuals. That's why we are tied down to the ground and can't fly. And third, the further the objects, the smaller the force of the gravity. Never zero. In space, there's very little gravity due to the distance of the large objects. This is called microgravity. Alright, and last but not least, gravitational attraction between the Earth and the Moon and the Earth and the Sun is the cause of a high and low tides. Alright, now we can calculate our problem here. So, calculate the altitude at which a satellite of a mass 2015 grams orbits the Earth. The gravitational force is 649 newtons, and the universal constant is, of course, 6.67 times 10 to the negative 11 Newton meters squared times kilogram squared. The mass of the Earth is 5.988 times 10 to the 24th kilogram. So, alright. So, we'll start off by writing our given. They give us our G, which is the 6.67 times 10 to the negative 11. They give us mass 1, which is the Earth, the 5.99. You can just round it up to 99. Times 10 to the 24th power. And mass 2, which is the satellite, of 649 newtons. Alright, and this, sorry about that. It's not the mass. The mass is actually 2015 kilograms. And our force was gravity is the 649 newtons. Or just, sorry. We're trying to find R. Not R squared, but R. Alright, so we'll solve this here. We already know our equation, which is FG, G, M1 and 2 over R squared. So in this in this equation, we'll just plug in what we have and we'll solve. 649 newtons equals our gravitation.
What happened to you?
167 times 10 to negative 11. Alright. And then mass 1. Then mass 2 over r squared. So, in this occasion, we can multiply r squared on both sides. And we end up having 649 times r squared equals all of this. We just bring it down here. And that multiplied equals 8.4101696 times 10 to the 17. Now that we have this, we can just divide 649 on both sides. Your r squared ends up being 1.295865 times 10 to the 15. Alright, it's r squared, so we'll square that. And our r, which is what we're trying to solve, is 8137.36 meters. Or you can convert this to kilometers, which is 36,000 kilometers.
Hi, Miss Rare.
Which is your more, could say general answer to answer in kilometers because of the large distance that we have. It's easier just to write this than the meters. But that's it. Thanks for watching.